Hello everyone, I am Shamran. Welcome to the channel. So in previous lecture we have seen the different criteria for shear force and bending moment. So in this video we will see that how to draw shear force and bending moment diagram for specifically cantilever beam. So today we'll focus on only cantilever beam, shear force diagram and bending moment diagram. So our first case study is cantilever beam subjected to point load, say W, at free end. So if this case study happens, so the figure we will draw first. This is a cantilever beam, say this is W, subject at free end, say this is AB of span L. Now if you are approaching for any semester examination, then follow this method. Also the GATE aspirants or any preparation for competitive examinations, you can follow this method, because the approach I am showing here, the writing part will be applicable for semester examination. No need to write this application part in any GATE point of view, or when you will solve this Sfd Bmd you will just have that calculation part. So number one will have find reaction. So for this case we will have our equilibrium equation summation Fy0 upward positive, because first we have to check in this loading diagram what are the reactions. So as this is a fixed support and this is a cantilever beam subjected to only vertical loading system, we'll have here vertical reaction, that is Ra, and a moment, that is Ma. Now Ma is internal moment, internal bending moment here, and Ra is the vertical reaction force. So to find this Ra, we need this equation. So if Ra is upward and this is downward, so Ra is positive because our sign convention was shear force upward positive, downward negative. So Ra is positive and W is minus W, that is equal to 0, because we are approaching from right side to left side. We have already told in previous lecture that I will proceed from right side to left side for the calculation part. So from this equation we have Ra is equal to W kilonewton, say. Now in second point you can write, considering a section XX at a distance small x from right end side. So here we are considering a section XX from extreme end B, and this distance is small x. Now number 3 is sign convention. So for shear force and bending moment we'll have our sign convention as upward positive, downward negative, and anti-clockwise positive, clockwise moment negative. So this is the writing part you can have in every single calculation part, but for the shortcut method you don't have to write this, you just only need to find the reaction and then you can proceed for the further calculation of Sfd and Bmd. So we'll have here a dotted line, we'll have the dotted line here. The number of points will be there, you have to draw this dotted line from every single point. As we have this A and B, we'll have this 2 number of lines. Now calculation of SF. I can remove this part. I hope you have written this. So calculation of shear force. Now to find the profile, I mean there will be a shear force diagram, there will be a bending moment diagram. To check what is the profile, I mean what will be the nature of that curve, will it be constant, will it be a linear, will it be a parabolic, we can find out by generalized equation. How can we find? We can find it by taking this same section. We have to find shear force at x, means about this point we have to find what is the shear force. So SF at x means we are considering only the right part of this section. So only the right part. What is shear force? Shear force is nothing but the algebraic summation of all the forces either at left or either at right. So we are considering here the right side. So in this right side we have only this W in negative downward direction. So we'll have W, but as the W is acting downward, we'll have this sign minus. So S of x is equal to minus W. Now here there is no x part. We have to get the power of x to determine what is the profile. So we are considering here x to the power 0. That means x to the power 0 means 1. As this is 0 degree curve, that means this will be linear. Now we will see a different case. If this is a point of W and this is a point, we will see this is just right of this point and this is just left of this point. This concept is only applicable for this point load. Now here just right, this load is not there. Say this is a beam, this is a point. Just right of this point, this load is not included. So here the effect of this load will not be applicable. Just left of this point, this load will be applicable for the calculation of shear force. Now here we will have like this. So we'll first write the points. So SF at B. First we have to check is that point is subjected to any point load or no. Here B is subjected to point load, so we'll have SF at B just right and just left, because B will consist of two shear forces, that is SFB at just right, SFB at just left. So just right, there is no inclusion of this load, so the value will be 0, and just left, inclusion of this W will be there, and due to downward direction this will be minus W kilonewton. Now after B we have to find which point we have to consider, that is A. So SF at A. Now have to check A is considered, have to check whether A is subject to any point load. Yes, this RA is also a point load because this reaction force. So due to this we have to consider here also just right and just left. So just right of this beam, we have only this W acting in this beam section. So just right, only these W will be there, that means minus W. And if we are considering just left of this point, then minus W will be included along with this RA, which is upward positive. So previously we have got RA is equal to plus W, so minus W plus W will be 0. Now have to draw this shear force diagram. So we have to point out at B we have 2 points, one is 0, then we have minus W. Below the ordinate we will consider negative, and up above this ordinate we will have this positive value. Then A will have minus W first, so this is W, and then it will be 0. So 0 to minus W, and again W to 0. This is negative. This is SF. So this is the shear force diagram for cantilever beam subjected to point load. Now what we will see, this is a constant shear force because only this load is there, so the constant shear force is developing here, there is no other any loading system. Now to find bending moment, we have to first check what is the profile for bending moment for a point load. For this case we have to find Bm at x, just like SF at x. So at X we have to find Bm. So what is Bm? Bm is nothing but the load into perpendicular distance from that point of consideration. So Bm at X will be, first you have to check in which direction the rotation is applied. Is it clockwise or anti-clockwise? So in our convention we have taken that right side of this section anti-clockwise bending moment will be positive. So right side of this section, this W is rotating in clockwise direction, in this direction. So that means this is negative, minus. So load is W and distance is X. So minus W into X. So here X, the power of X is 1. That means this is also linear. Now, in the same way, we have to find Bm for different points. But this just right and just left consideration is only for shear force calculation, not for bending moment when only the load is applied. If in this system any other external couple is applying, for that case you can consider bending moment just right and just left. That part we'll discuss later. Right now we will see bending moment at B, because how much in point B and point A there will be only bending moment. So bending moment at B and bending moment at A. So in B there the load is applying, but the point itself, the distance is 0. That means this is 0. So at B there will not be any bending moment. For cantilever beam, as this is the fixed support, all the load is applying here. So the fixed support will try to resist this beam. So the maximum moment, this here, maximum moment will be generated. So Bm at A, the value of moment, what will be the value of moment? First we have to check in which direction the load is applied. So this is clockwise direction, our convention is anti-clockwise positive. So this will be minus load into distance. How much distance? The total span is L. So L, that means minus W into L. So if we draw the bending moment diagram, here the point bending moment is 0. Here this is W into L, that is negative. So the profile will be linear. So this is negative. This is the bending moment diagram. So you can see the moment variation is here 0 and it is increasing and its maximum in the support portion. So fixed support will have maximum bending moment for cantilever beam. Now we will forward with the next case study, that is cantilever beam subjected to uniformly distributed load. So in the next case studies will not have this writing part, will have only the shortcut part, and we will have to find the reaction only, and we will find the shear force and bending moment, and we will draw the diagrams. So the next case study is cantilever beam subjected to uniformly distributed load throughout the span. So if this is a cantilever beam, throughout the span UDL is applying. So this is W, say kilonewton per meter of span L, and this is A and this is B. So first of all we need to find out RA, and here MA will be developed. So to find RA, we will have our consideration if Y is equal to 0, upward positive. So for this case RA is positive and this total load is downward. Downward means negative. So as this is the intensity part, we have to find the total load. To find total load, W into total distance, that is L. That means its units, it's kilonewton per meter, and this is meter. So meter gets cancelled. This value is kilonewton. So that is equal to 0. So RA will be equal to small w. Now we'll find the shear force. So SF. So in this case there will not be any consideration of just right or just left. We'll only have to find out the shear force at that particular point. So SF at B will have SF at B and SF at A. Now Sfd B means if this is a UDL, say if this is a UDL, if I am considering this point, this is the ordinate, that is W kilonewton per meter, but this is distributed throughout the span. This point doesn't consist any of that load. If we go through this span, and after going through this span we are getting here, and we'll consider this point, we'll have our total loading system. So in a particular point, if there is no effect of any load, we can have a zero shear force. So here there will not be any shear force, I mean any internal resisting force. If we consider or move forward from B to A, we will see this whole loading system is applied in the B. So in that case, if we find out at Sfd A, now we have to check A is subjected to a point load. So there will be a consideration of Sfd A just right and Sfd A just left, because this point load is applying here. I mean, this is a reaction force developing here. So just right, only this UDL part is there, this is downward. So downward force means negative, and total load means small w into L, that means minus WL. And just left, this minus WL part is already existing, and after just left, this RA is including with this part. So RA is upward, that is why plus RA, that's minus WL plus RA means WL, that is equal to 0. So we'll have our all shear force values for these points. So at B this is 0, at A this is WL, and then again it is 0. So this is a value. Now what will be the profile? Will it be linear or parabolic or cubical? We don't know. So to find out the profile, we have to again take a section x at a distance x. So we have to find out Sfd x. So what will be Sfd x? Right side of this section, this is downward force. Downward force means negative into total load. Shear force means only load, total load. So total load means small w into this distance x. That means minus wx. So here x have a power of 1. So this is also linear. So this variation will be linear variation negative. So this is Sfd. So by seeing this diagram, we can see there is no load. Here maximum shear force is developing, and this is linearly developing. Now we will start with the bending moment. So Bm, here 2 points are there, one is B, another is A. So Bm at B and Bm at A. Now what will be Bm at B? So B, here B, there is no effect of load, that is why this will be 0, and unit will be kilonewton meter, as load into distance, that is kilonewton meter. Now Bm at A, the whole effect of this load will be here in A. Now right side of A, there is only the UDL part, and this is trying to rotate in clockwise direction, that is why in our convention this will be negative, and the value will be load, that is small w. This is load intensity, that means we have to find the total load, that is W into L, and the CG distance, that is center of this span, that is L by 2. So multiplied by L by 2, that is equal to minus WL square by 2. Now we have to find out, as this shear force diagram is in linear concept, so in bending moment diagram, what will be the profile? For that case, just like this Sf at x, we need to find out what will be Bm at x. So in this section xx, take the moment about this section. Similarly, this load is trying to rotate in the clockwise direction, that means the sign will be negative, and total load will be load intensity W into x. This is total load multiplied by distance from this section, that is distance from this point, that is x by 2. 2, because for this certain load the CG distance will be midpoint of this load from this section, that is x by 2, that means minus wx square by 2. So we have x power 2, that means the profile will be parabolic. Now we have find out the profile. Now we can draw the bending moment diagram. So put the value at B, that is Bm at B is 0 and Bm at A is minus WL square by 2. So minus means this ordinate WL square by 2. Now the profile is parabolic. Now we have to know a new concept. If this is a parabola, then we may draw like this or like this. Now which we will find that which type of parabola we have to choose. So depending upon, say the previously we have derived V is equal to dm dx and small w is equal to dv dx. That means this shear force slope depends on this w and this bending moment slope depends on this value of shear force. Now in this diagram the shear force value here is 0 and here the value is increasing. That means the value SF value here is increasing. That means bending moment diagram slope will be also increasing. Now slope will be increasing, that means if we choose this figure, then here the slope, how we draw slope? To draw a tangent in some point. So here theta is equal to 0 and here we have theta is equal to maximum value. So 0 to maximum means the slope is increasing and here the slope has a maximum value and here a slope has 0. That means it is decreasing and it is increasing. Now as in this case the SF value is increasing, that means BMD slope will be increasing, so we need to choose this figure. So by showing this SFD value we can conclude the BMD diagram as this. So maybe we have lots of doubt when we draw this BMD diagram, or as this is parabolic variation, so this will be this like or this parabola like. So we can find out this BMD parabola profile by seeing the shear force value, whether it is decreasing or whether it is increasing. Similarly, if we find this SFD slope, this slope is 0 to WL means the slope is increasing. Increasing means, that means here the load is 0 and if we go right to left the load effect is increasing. That means as the load intensity increasing, the SFD profile is also increasing. This is the whole concept behind this cantilever beam subjected to UDL. Now we will focus on cantilever beam subjected to uniformly varying load. UVL, uniformly varying load. So if this is a cantilever beam, the UVL is subjected like this. So here the maximum load intensity small w and the span is L and the beam is AB. So for semester point of view you can approach like that writing part. We will start here in some shortcut like finding out the reaction, that is here the reaction will develop RA, that is summation Fy is equal to 0, that is upward positive. Here RA is upward, that means positive, and this whole load is downward, that means negative. So the total load, in our previous video we have seen how to find this total load. See this video, that is half into small w into L. This is the total load, that will be equal to 0. So RA is equal to WL by 2. So for UVL, to find the total load we have to find this enclosed area. So area means half into this W into this L. So WL by 2 kilonewton. Now we have to find out the shear force. thus we can draw this dotted line. Now SF at B, first check whether B is subjected to any point load or not. Here there is no point load, so we have only one value of shear force here. And SF at A, here check whether any point load is there. Yes, RA is there. That means SF A will have a just right value and a just left value. So found SF at B. So here B, there is no load. This load is applying and the effect will be considered here, not here. At point B there is no effect of load, that is SF at B 0, and SF at A, just write point A, the whole load effect is considered. That means this load is downward direction, so minus the total load, that means this area, that is half into W into L, that is minus WL by 2. After considering this RA, that means if we go further just left of this A point, this minus WL by 2 will be included with this RA. We have already found out the value of RA, that is plus WL by 2, so that means this is equals to 0. That means this calculation is okay. Now we have found out that SF at B is 0, SF at A, just right value is WL by 2, and finally it is going 0. Now we have found out this ordinate. Now what will be the profile? For profile checking, let's make the similar process like taking a section XX at a distance x. Now we have found the previous case, what will be the profile for UTL. Now we'll find out what will be the profile for UVL case to draw SFD and BMD. Now if we take this section XX at a distance AX, we have to find out this total load area. That means SF at X means right side of this XX section there is nothing but this only UVL part. So this is minus, as this is downward, total load. But to find this total load we have this X, but we don't have this ordinate value. So to find out this ordinate value, let's take this value as Y. So we have to find out what is Y to get this value, because SF at X means minus half into Y into X. This Y is this ordinate value. Now what is Y? From similar triangle, this triangle is equal to this triangle. That means if this by this, that is small w by L, is equal to this Y by X. From this we can get Y is equal to small w X by L. Now we can substitute the value of Y in SF at X, that is minus half into Wx by L into X. That means minus half Wx square by L. So here we get a power of 2, which defines parabolic profile. So for shear force diagram we have got the parabolic profile. Now the same case, we have to find out whether this parabolic slope will be increasing or decreasing. So check out, this value is, the load intensity value is increasing here. So the profile will also increasing. That means the slope of shear force profile will also increasing. And increasing slope means this, because here theta is equal to 0 and here theta is equal to maximum, because if we draw a tangent here the slope will be 0, and after this profile is increasing and here a slope will get, that will be maximum. So this is negative and this is SFD. Now we'll find out in the same procedure what can be the value of bending moment. So now to find out the bending moment, we'll have 2 points, that is BM at B and BM at A. Now there is no load here at B, that means the BMB will be 0, and in A the whole effect of this load will be there. So about the point A we have to take the moment, and right side of this A point we have only this UVL acting. So this UVL acting in downward direction, that means it has a tendency to rotate in clockwise direction. That means the sign will be negative, as our moment convention is anti-clockwise positive and clockwise negative for right side of the section. So Bm at A will be minus total load into distance. So minus total load multiplied by distance from A. So which distance? That is CG distance from A. So this will be minus total load, means this whole area enclosed by this UVL, that is minus half into small w into L multiplied by distance from CG. Now in previous video lectures we have already seen what is the CG for this case. As this is the base of this triangle, we have the CG value 1/3 of this L. If you consider the vertex, then that will be 2/3 of L. So as we are considering A, this is a base point, so from base this CG value will be L by 3. That means minus half WL square by 3, that means minus WL square by 6, that is kilonewton meter, if we have put this unit. Now similarly we need to check what will be the profile for bending moment diagram. Now similarly we can take the bending moment about this section XX. So Bm at X, what will be the value? We have the value of this ordinate, so it's very easy to find out the bending moment at X. So this load has also a tendency to rotate in clockwise direction, that means the value will be minus, then the total load will be this area, that means minus half into y into x, and from this point, this is also the base for this small triangle, so from here the CG distance will be x by 3, means somewhere here. So this is x by 3. So minus half into, substitute the value of y, we have already found out this y as wx by L. So here minus half into wx by L into x by 3. So we get minus wx cube by 6L. So x has a power of 3, that means the profile will be cubical. So similarly we can check whether this cubical profile will be like this or like this. So we have to find out what is the shear force value, is it increasing or decreasing from right to left. So we can see here the value is 0, we got the shear force value here 0, and here it is WL by 2. That means 0 to WL by 2 means it is increasing. So the value has a tendency in increasing nature, that means the bending moment diagram profile will be an increasing slope. So increasing slope means this will be also like this. So this is negative, this is 0, and this is WL square by 6. So here the slope will be 0, and here if we draw a tangent, here we will get theta is maximum. That means we can conclude just write this down. If you have any doubt to solve what will be the nature of this profile, or is it increasing or decreasing, just remember this point. This will help you a lot for finding this SFD and BMD diagram in a fraction of second. So load intensity value directly depends. That means load intensity, if the load intensity value is increasing, SFD slope is also increasing. If load intensity value is decreasing in nature, SFD slope will be also decreasing in nature. SF value if increasing, BMD slope will be increasing in nature. SF value if decreasing, BMD slope will also be decreasing. These 4 points are key point. If you want to practice some more questions about this cantilever beam. These are some questions, the link are given in the description box. If you have any doubt or if you want to get the answers of these questions, mail me at this mail ID. So if you like this video, don't forget to hit the like button, and if you are new to this channel, don't forget to subscribe. Thank you for watching.